Okay, so this is a very old slide of mine. So just to remind me that this course is being started, this course has been started in 2008. So I keep these slides to remind me. So it has been around 13 years. Okay, so we will see the one technique which you are first going to apply in your lab, that is the model checking for verification and validation. So as far as the model checking is concerned, it's an automatic technique for verifying finite state concurrent systems. Okay, so we will see that what is this finite state concurrent systems and how we are going to make them. So you have studied DFA. So in automata theory, so we will see like there is going to be transition systems, and then there is going to be a label transition systems that we will study later on. Right now, what we will see is basically how we are going to build a model actually uh, in any language. The language which we are going to use is actually CCS. We will see in a few minutes. CCS has got just pretty simple 5 operators. So you can learn them in not more than 10 or 15 minutes. But to be proficient with all those operators and use them properly probably will take a semester. So, but I'll tell you how you are going to make a model using that CCS. Okay. So model checking is basically comprises of 3 parts, and these 3 parts are a framework for modeling a system. That means you will be having a framework or a tool, like you have got a framework in object oriented systems. Okay, here also there is going to be a framework or some tool, you can say, over here, uh, in which we are going to actually write our code, our model, and then our properties. Okay, and then that framework is responsible for verifying that. And then we are going to have an specification language supported by that framework. What's your framework we are going to use? It is going to support this specification language in which we are going to describe the properties to be verified. And just a minute. I'm sorry for a small interruption, but so a specification language for describing the properties to be verified. So we'll see today itself what is a specification language in which we are going to write. And then there will be a verification method. That means we will be looking in the framework itself, not today, but later on we will see on the basis of what logic we are saying that this system specification actually has been met into the implementation. Okay, so there should be some verification method. Verification method could be just through theorem proving. If we are doing so there are going to be certain statements which are going to make the premises, then we are going to go to the conclusion. As far as the model checking is concerned, in this we are going to have state space search for a certain property of the system. If in a certain state certain property is going to hold, then we say that this is the property which I was looking for. How all these things are going to happen, we will be doing it in detail. So if you are not able to understand really what's happening, then don't worry about that. Right now you have to focus how you are going to write expression using CCS, and then how you are going to use the properties using some logic. And then given these two things, a specification or a model and this properties, to the tool. The tool is going to say that whether this property is going to hold on this model or not. That is your job. If you are able to see this property holds on this model, true, that means property is holding into that model or in model of a system. Otherwise, it's not going to hold. If it is going to say false, then actually we have to look where in the model or in the property I have made the mistake. That's what our focus will be. So if you are able to understand this much in next half an hour, then it's enough, not more than that. So here in model checking, we will be saying, so model of a system of architectural design or any model of any system is going to be given to this model checker. So this is the framework, you can say, model checker. So CWBNC is a tool. In your lab, you will be asked to install this particular tool on your machine or on your laptop, and then to this CWENC, you are going to input a model, which will be a .ccs file. So you will be load some abc.ccs to this model checker prompt. That means to this model checker, and then some property. Okay, that means .mu file to this. Again, you are going to load abc.mu file. So that means you are giving this input to this tool, this model checker, and then after you have given these two files, then you are going to write certain commands to check whether this property, like check property P1 on this model, some model. Okay, so if that property is going to, this property which you are trying to check is going to be true, then you are going to find true. And if it is false, then you will be getting a false, that this property is not being satisfied, and then you will be getting a error trace for that. So that's all what you have to experiment in probably the next lab. If you have done any lab, then probably your instructors might have asked this to you people. Okay, so this is what probably you have to do. So the language for describing the model I am going to use is the CCS. CCS stands for the calculus of communicating systems. Okay, so this is calculus of communicating systems, that is the CCS. And this is a process algebra developed for analytical modeling of concurrent communicating systems. So there are going to be a concurrent systems, and these concurrent systems has got several parts, and they may go independently, and sometimes if need be, they are going to communicate, send messages to each other. So we need not to be worried about what all these things are, but just right now CCS is a process algebra, and how we are going to use it. Remember, CCS considers a system as a network of components which behave according to their specification. So we will define certain components, and then we have got operators to combine those components. So any CCS specification will be the basic actions along with combining operators, through which we will be making CCS equations. And in a moment, we will see how we are going to do. And each part is known also as an agent in the CCS expressions. And agents are supposed to communicate with each other via ports. So what are going to be the ports? We will see. Any action through which I am going to model a system is going to be considered as a port. Okay. So as you might have seen a port in your network systems, these ports are nothing but certain actions, okay, through which we are supposed to model a system. So remember, so if you are going to model any system, that means you are supposed to model a behavior of that particular system, and behavior can be best modeled using the actions performed by that particular systems. Okay, so if you are supposed to model the behavior of any system, so you generally think that particular system in terms of its behavior. Okay, so talk about any system. Supposing you are going to look at your wristwatch. Okay, then your wristwatch, what is the behavior of this particular wristwatch? Basically, it is going to tell you the time. Okay. So, and if you look at the action, what is the action in the older wristwatches? Tick could be an action because it does tick, 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 tick. So every tick is going to advance the clock by 1 second. So you can write the clock as clock is going to be something which is going to tick. But that is not the absolute definition. In your model, clock is supposed to be defined by, clock is going to be defined by tick dot clock. Okay. So maybe just after a few minutes, I am going to use this my board, writing board, to explain if these things are not going to be clear to you. But till the end of the class, if the things are going to be clear, then probably I will not use that. But let me see that whether the things gets clear or not. Okay. So here, if I say there are going to be certain operators, as I said, into the process algebra. So if particular action, supposing there is going to be a tick action in a clock. So this alpha is corresponding to tick. If I say alpha dot E, so E is supposed to be an expression, an agent name. Okay. So alpha dot E, that means supposing there is a clock. So clock will be defined like it does tick operation and becomes a clock. So after doing certain things, something becomes something. Okay, what do I mean by something becomes something? After studying, you become a student. When you study dot student. Okay, or if somebody is teaching, teach dot teacher. So depending upon which kind of action you are going to perform, you are going to be defined as an agent of doing that particular thing. Okay. So you know generally everybody is going to be defined by its behaviors. It's be carpenter, blacksmith, in any profession. So these people are going to be defined by the use of actions, what actions they perform. So similarly here we are saying this is alpha dot E. So alpha is an action over there. Then there is going to be a summation operation. It says if you have designed one agent like alpha dot is, another agent as beta dot F, you can sum these two agents. So alpha dot E and beta dot F, these two agents can be a summation. Summation is non-deterministic choice. So either alpha dot E is going to be performed or beta dot F is going to be performed. Both of them cannot be performed simultaneously. We will see this just in few minutes. Then there is going to be the composition operator. E1 is going to be composed with E2. If there are going to be two agents, so E1 and E2 will become the composition. The system is composed by two things. And then there is E slash L. This is the restriction operator. We will see whatsoever actions are going to be there into L that are restricted into E. So those actions are not going to be observable externally if they are going to be there. So F is going to be a relabeling function. If you want to rename certain action in certain agent or in certain expression, you can define a relabeling function. Okay. Don't worry if these things are not making perfect sense to you at this point of time. I am a little bit in a hurry just to teach you these things so that you can start something in your lab. All these things will be discussed in detail when I will be coming to the CCS, when I will be coming to the logic properly. But for this moment, I am trying to enable you. I am trying to make you be able to write some code in CCS and write some property so that you can see, you can execute, or you can start doing something on your own in the lab. Okay, so how I am going to write these things, I am going to use these things. Probably you can understand this by this example. So supposing there is going to be a vending machine, and we are going to define this vending machine using the operators of the CCS. So what are going to be all actions into this vending machine? Supposing actions are going to be you have got a slot to insert 2 paisa coin and 1 paisa coin into the vending machine. So you might have seen a lot of vending machines where you insert money and you get things. But this machine is a model or hypothetical machine. For that only I have taken 2 paisa, 1 paisa. Otherwise you will not get anything by 2 paisa, 1 paisa right now. And it is not even valid 2 paisa, 1 paisa. Okay. So big chocolate costs 2 paisa and little one actually costs 1 paisa. And then here only 2 paisa and 1 paisa coins can be used in this particular machine. So slots has been defined like 2 paisa, 1 paisa can be an input to this machine. Okay. And then there are going to be 2 buttons, big and little. So if you insert 2 paisa, then another action, big button can be pressed or big could be pressed. So inserting 2 paisa, if you are going to press the big button, then you have to collect the big chocolate. Okay. If you have inserted 1 paisa, then you can press the little button. You can collect the little chocolate. Remember, the way you are going to define the behavior of this machine. Okay. So the behavior of the vending machine is going to be defined like this. B is defined 2p dot big dot collect dot b plus 1p dot little dot collect dot b. If this is the behavior, so remember 2p is some action, basically input action which is being performed on this particular machine. 2p, 2 paisa is getting inserted. Big is some action which is performed on. So this machine is actually made of only these actions. Okay, so if if you want this kind of behavior, then this machine is going to be defined in this way: 2p dot big dot collect dot v, 1p dot little dot collect dot v. But if you want to change the behavior, supposing if you want to say like how it matters, we are 2 friends and we have got 2 paisa. We want to insert 2 paisa and we want to get 2 little chocolates. So just uh, just a minute. हाँ क्लास में है बोलो क्लास में है बोलो I'm sorry. So what I mean to say is you were 2 friends and you had 2 paisa and you wanted 2 little chocolates. Okay. So you can change the behavior of this machine by writing one more plus. So what will be, by this you can add plus and then you can write 2p dot little. That means you are pressing 2 times little after receiving 2 paisa, and then you can do collect and then again collect. Or you can say 2p dot little, then dot collect, then again dot little, then dot collect. If these actions are allowed, so the behavior of the machine will be defined by your sequences of actions which are available. So we have used actually these actions to be big and then we have sequenced them. That's why this is called alpha dot E. This dot operator is called a sequencing operator. So any sequential process can be written using this dot operators, that is the sequencing operator. And then if you are going to sum it up, that means these are all alternative behaviors which can be built into this particular machine. And you can probably build this machine in various different ways. Like you are going to insert 1p and then press big and then collect, isn't it? You are going to say 1p dot 1p and then press big button and then collect the big chocolate. Then you can say I can also use the combination of I have just inserted 2p and then 1p and then I want certain operations to do. So whatsoever operations you want to define, you can define with the plus operator into the vending machine. Okay. So whatsoever behavior, in whatsoever way you want your this vending machine to behave, you can incorporate all those behaviors into this vending machine. I hope the things are going to be clear to you. So all those behaviors which has been incorporated over here can be actually checked with certain model logic formula or with certain Hensi-Miller logic formula to ensure that really these behaviors are going to be there into the system. So I hope you have understood how you are going to write a specification using a process algebra CCS in pretty simple way. Okay, so this is we have looked at only two operators, that means 2p sequencing operator and this plus, that is the non-deterministic operator. So all these are behaviors which are alternative behaviors, and machine, depending upon its input, what kind of input and what kind of actions buttons has been pressed, will take one of these paths which are available there into this machine, are one of these alternatives. What I mean to say, if you are going to, in this particular machine itself, if you are going to insert 2p, that means then the first part is going to be taken. If you are going to insert 1p, then definitely second part will be executed, or second part will be taken. And if you have inbuilt many other alternative behaviors in this machine, then definitely, depending upon what sequence of actions you are performing over this machine, what sequence of behaviors actually is being operated in this machine, depending upon that, we are going to take and one alternative. So this is a non-deterministic choice. Why it is a non-deterministic choice? Because beforehand we don't know. It depends upon the environmental input. Whatsoever input is coming from the environment is actually going to decide which part of the vending machine is going to be actually be in execution, or which part is going to be actually taken. Okay, so because it's dependent upon the external environment. Okay, so this is simple how we defined it. And then I am saying there is going to be a model mu calculus, but I will not be discussing this part at this point of time, model mu calculus, but I will do this particular thing in Hensi-Miller logic after this description of the system. Okay, so I am skipping this and skipping this because it will be a little bit difficult to understand at this point of time. I will come back again over this. Okay, so I will take one more example how we are going to model the system into the this CCS by taking the example of the okay, proxy server. All these properties can be written. I'll explain this after a few minutes once I have done the Hensi-Miller logic. I'll come back to this slide again. Okay, so don't worry. All these things is going to be explained to you today itself. And you are supposed to be writing this kind of property which are going to be satisfied upon this vending machine. Okay. So next is example I am taking where that is you are going to model a proxy web server using CCS. Okay. So here we are going to model a web proxy pattern using a CCS. So proxy, as you know, so what is proxying? There is going to be a certain client. It is going to send a request. Okay. And request is going to be received by a proxy. So here now you have to familiarize yourself with certain CCS terminology. That means these client, proxy, and server are supposed to be working, are supposed to be behaving as an agent. Okay. And every agent is going to be written in terms of the actions of itself. So in CCS, client is going to be written by its own actions. So client can send a request and client can receive an answer. So client would be written like client is defined request, it outputs request and it receives an answer. So wherever there is going to be the overbar, okay, overbar shows that this is the output action. And if there is no overbar on certain action, then this is going to be the input action. Okay, remember this. So client outputs the request and receive the answer. And then this request has been received by the proxy. And then what proxy does? Proxy receives the request, and if it has got an answer, then it is going to send the answer, isn't it? So this proxy is going to receive the request and going to send the answer, and then again become the proxy. Recursively, it behaves like that. If it has not got an answer, then this request is going to be further sent to the as a request to the server. So it outputs request to the server, and then server is supposed to reply, isn't it, over here? But this reply from here is not going to be the part of this proxy, isn't? Because as I said, this proxy is going to be defined in terms of its own actions only. So the proxy has got only 4 actions. It receives request, it outputs request, it outputs answer, and it receives reply. So it will receive a reply, and then it will, after receiving the reply, it will send an answer to the client. That will become the proxy. And server is pretty simple. Server is going to be defined as it is receiving a request, and then it is going to send the reply. Okay, now once I have got the client, proxy, and server, then whole of the system's architecture can be actually realized by the composition of these client, proxy, and server. So you can compose this architecture of the whole system by client, proxy, and server, and it is going to behave that way. Okay, so 3 operators today I told you. First one is the sequencing operator. Second one is the non-deterministic operator. Third one is the composition operator. Composition operator, what it does is, you have defined various component of the systems in terms of its actions, and then they can be composed together to work as a whole. I hope you have understood this part. Okay. So when you will be defining, you will be defining this kind of a system. And then there are going to be certain properties which has been written over here. I will share the slides. So for the starting, you can write these properties and you can execute on the CWBNC, because you can see how it runs. So invariant properties of the proxy pattern has been given over there, but I am not going to explain it right now. I will explain it after just few minutes. Okay. So I hope you have understood. If not, appreciate it fully, then probably you can look at these slides. I am going to upload it just after the lecture. You can see it. It may be useful for your lab as well as for your theory course. Okay. So now the third part, the final part of this lecture is I am going to discuss this Hennessy-Miller logic. So what is there in this? This is a simple logic. So I told you, any system that you want to verify, first you need to write an implementation. So implementation is supposed to be written using the CCS, as I shown you that you have the vending machine implementation and you have the proxy, web proxy pattern implementation. Then if you want to write a certain property of that particular system, so for writing the property of that system, you can actually use this Hennessy-Miller logic. Hennessy-Miller logic has been made by 2 prominent scientists of computer science, that is the Matthew Hennessy and Robin Milner. Okay, so these 2 people made a logic, and this is a pretty simple syntax. As far as syntax is concerned, this is BNF syntax. So any valid formula in this logic is nothing but true, that is the TT is going to be the literal, and false. So you can say true or you can say false, FF. Okay. So it items of this logic, okay, very smallest item is going to be true and false. By using this true and false, you can actually build certain formulas. Okay. And remember, so if you have written any formula using true and false, and these actions, whatsoever actions I am going to explain to you, so these actions are nothing but the actions of the CCS expression itself. So here, as far as you are looking at box modality, I say, which is into the big bracket, and in angle bracket, I am saying this is diamond modality. In box, you can write any action, like we had action 2P, okay, and we had action 1P, we had action big, we had action little, we had an action request in case of the proxy. So in this way, we are supposed to write this particular formula. Okay. So think about if you are going to write, so smallest unit of this logic is true and false. Okay. And it is supposed that if we are looking our CCS or our state machine, then every state satisfies true and no state satisfies false. That means false is false in every state, false is nowhere true, and true is true in every state. So, okay. And then we can combine. So once we had got TT, and then we can add TT with certain action. Okay, so TT could be one simple formula, that is Z, I can say. And then when I write box modality ATT, you are getting box modality ATT, then it will mean something. What it means is we are going to discuss. Okay, so if we are saying F and G, and they are going to be some logical formulas. Okay, so what is semantic? Syntax is this one, supposing I was looking at. And then what is the semantics of this? So P means any process satisfies FF. If there is going to be any state or any process which is satisfying FF false, it means P belongs to phi. That means there is no state. P belonging to phi means there is no state which is going to satisfy this FF. P satisfies T2, TT, that means P is satisfying all the procs. That means P is satisfying all the states. P satisfying TT means P belongs to the states of all the processes. So if you have got 10 states in any system, TT will be true in every state. Okay. And then P satisfies AF means whenever P satisfies A, if there is an action A in a state and I am reaching into another state where F is going to be true, okay, then box modality AF will be true in the starting state. That means there exists some state Q for which if I am performing an action from P to Q by A, okay, then if F is true in state F, then this box modality AF will be true into the state P. Okay. And box modality AF means, that means whenever I am going to perform an action A in whatsoever state I am, then it is going to be wherever I am going to be, F should be true. Okay. So for every Q. So okay, so let me explain this. If you have understood this FFTT little bit, I am going to take an example. I will take further example as well. So let's see. Supposing I say, does P satisfies CF? So here, think about it. There is going to be a state machine, you can say. So P is going to be one state, Q is going to be another state, Q dash is going to be another state. From P, I am performing an action A and I am going into Q dash. From P, I am performing an action B, I am going into the Q state. Okay. So just imagine that if if what happens, if instead of C here, I am going to write B, okay? Instead of C, I am going to write B. So if you are writing here, Q does not belongs to the semantic value of F. That means this Q, and here Q dash also does not belong to the semantic value of F. That means it doesn't satisfy F. Here F is not satisfied. Then uh, B dot F will be not satisfied into the P formula. But CF, if I say CF, CF could be satisfied because there is no C action by which I am going into the Q. Okay. So if it's not clear, let me actually connect my, just hold down a minute. I will explain it through. So just hold on. Okay, so here CF is satisfied, but all these I will explain you some later point out. But first, let me explain this formula. So what I am going to. Just a minute. I am connecting the device. Okay. So is it visible? Hello?
No, sir.
Is there, just a minute. Okay, so let me share this. Now screen is visible.
Yes, sir.
Okay, so those actions which I was talking about, just remember, just a moment. Okay, so I was talking about supposing I am writing a certain formula in this way. So supposing this is, I am saying, yes satisfies. Mind this is something yes satisfies. Okay, I am saying I am writing box A 5, where 5 can be considered as F or something like that. Okay, so it says yes satisfies this diamond modality. This is in angle brackets. Whatever action I am writing, this is going to be known as an uh, diamond modality. Okay, and then phi says that somewhere I am going, there is going to be a state where phi holds. Pretty simple formula for phi. Phi could be even tt, like I so said, tt and true. Okay, true you can say. So I said, like, supposing there is going to be a machine, supposing there is going to be some states, this is going to be yes, and from yes I am going to take an action A, and then I am going to into another state that is actually yes dash. Okay, so if in yes dash, supposing I say either phi, if I want to say there is going to be certain formula phi, supposing I am written phi as TT. TT means true. So as I said in the starting, this TT will hold or true will hold in all states. So here also true is holding, and in this state also true is holding. Okay, true is holding in every state. So if I say, if I write this particular formula, that yes satisfies box modality A, and then I have written TT over here. So what it all says is, if I am in state yes, okay, and I am going to take an action A, some action A, by action A, I am going to be in yes dash. In yes dash, true should be holding. So I am in state yes, I am taking a transition by A action to another state. If true is holding in every state, so definitely true is holding over here. What I am saying is this yes satisfies. ATT means this formula ATT, whole formula, whatsoever formula has been written, this ATT is going to be holding over here into yes state. Why this is going to hold into this state? Okay, true, because we are saying this formula ATT will hold in the state, okay, in which state, where after taking an action A, wherever I am reaching, this TT is going to hold. So this way I can build the formula. Even I can increase this by writing A and then writing B and TT. So what will be the transition system on which this formula is going to hold? So I can make another transition system, okay, where this formula is going to hold. So what will be the transition system where this formula is going to hold? So I have state yes, and then by performing an action A, I am going into yes dash. Then by performing an action B, I am going into yes double dash. Definitely, I am saying TT is going to be true in all the states. So TT is going to hold over here. Okay. If TT is going to hold over here, that means then BTT is going to hold in this state. And if BTT is going to hold in this state, then A BTT is going to hold in this starting state. Okay, so I hope you have understood this diamond modality. That means you are in a certain state, and from that state, if you are performing certain an action, then wherever you are going, if the final formula is going to hold, and remember this formula ABTT can be defined as F. Even this could be treated as an F. And then if I say box modality AF, that means then from where I will be coming. So if I am saying box modality AF, where A, B is TT is going to be, I have said this box modality A, box modality B, TT. So for this to hold, what kind of system I should have? I should have one more state over here. This is where AF is going to hold, isn't it? This is F. So that means I have A already, and then I have B over here, isn't it? And then F means box modality A. And if over this state, supposing if I am saying now I am looking for this formula, where this formula will hold, then I have to actually add one more is over here A, and then I will be saying this is the state, yes, minus I can say, where box modality AF is going to hold. Is it clear to you? So how this box modality is actually working? So, I'm sorry, diamond modality is actually working. So, diamond modality is saying any formula, wherever I am going to. So, how we are building the formula, we have already said that any Hennessy Miller logic formula, HML, जो भी, whatsoever formula is going to be there, this is going to be either TT or EFF first. Okay. And then we said TT, with the help of TT and FF, we are going to write FRZ or F and Z. Okay. FRZ and F and G. And then we are further said that this could be AF or this could be a box modality AF. So we have understood little bit about what does it mean by this box, see this diamond modality AF, if you have understood. So diamond modality AF says, now we can go a little bit further, elaborating on this. So what do you
Five.
think if, just a minute. Tell me, you have some question. Jayate.
Time is over.
Yeah, time is over, but uh, I'll just finish in not more than 5 minutes. Just okay. So if I say this particular formula, which formula? Supposing I have written a state over here, and in this state, what's going to happen? This is going to be A transition, and this is going to be another A transition, and this is going to be a B transition. So, what do you think as far as the diamond ATT is concerned? It will hold over here or not in this state? So diamond ATT says that there exists a state, okay, there exists a state if I do an action from there and then wherever I go, TT will hold. Okay, so here box ATT, even if there is going to be a single state, then this here, this diamond modality ATT will hold. Okay, you are getting this point. And what about box modality A? It says whenever an action A happens, supposing I say here, I am taking an action A and I am reaching over here and I say F holds over here and I am reaching by A over here and F does not hold over here. Does not hold means nothing but F is not true in this state. Then if I say diamond modality AF, it will hold in this state. This is true. But if I say box modality AF, so this will not hold in this state. Why? Because it says whenever an action A happens, wherever I am going, F should hold. So box modality says for all actions A, wherever I am going, F should hold. And diamond modality says that if there is going to be only one branch, wherever I am going, if F is going to hold, then it is going to hold. Remember, it doesn't have to do anything with any other action. If instead of A, supposing I say here, this is action A, and then I am reaching, sorry, here F is holding. And then if B is going to be there over here and F does not hold in this state. Okay, does not hold means F is not true over here. Then what all, if I have to say like box modality A, F holds or not, it will hold over here. Why? Because I am only caring about the actions, that means box modality of A. Wherever I am going after performing an action A, F should hold. I have performed an action A and I don't care about B. You got this point? And then further, what we can do is this formula can be further elaborated if I write it like this. If I have, supposing A, uh, in the bracket, I have got box modality B, true, plus, sorry, not plus, rather than and C, true. If you are going to write certain formula like this, then this is going to be actually holding on the machine. Okay, on which machine? Supposing this is a state yes, and from here I am performing an action A, and then wherever I am going in this state, I am going to into two states, and there should be B and here should be C. And in this state, both state definitely the true is going to hold, because this state also true holds, this state also true holds. Okay, so this state will satisfy this formula. So can anybody tell me, if I am going to make this machine, I am going to make this model. So this is a formula, this is a logical formula. Okay, so this is going to be known as an specification. And for this is going to be a model which is satisfying this formula. And then if I am going to write this like this, I am performing A, I am going somewhere, and then I am performing B, I am going in some state. Then I am performing A over here again, then I am performing C over here, and I am going over here. So if this is going to be the model, okay, so if this is model which you have built, whether this formula diamond modality A, diamond modality B true and C true will hold in this state or not? Anybody? If you have understood, then you can answer actually. It is going to hold in this state or not? Okay, it will not hold. Why it will not hold? Because if you remember, after A, we have got a bracket. Wherever I am reaching, B true and C true both should hold. But here, if I am performing an action A, I am reaching into the state where only B is going to hold. Here, no C holds. Here, only C holds. There, no B actually holds over here. Okay. So if things are clear, okay, as far as this formula, simple formula is concerned, on the basis of this only, we have written actually the formula of vending machine. Okay. So if you have understood little bit about this, then probably let me show you that slide here that I didn't explain you. So if this is the expression 2p dot big dot collect dot v, 1p dot little dot collect dot v, in terms of these actions only, I am going to write certain formula this 2p. That means wherever I am going to insert 2p, and then I am going to press big button, then I am going to be there is going to be a TT. Okay, so this property should be satisfied upon this vending machine. You are getting it because it is 2p dot big dot collect dot v, but 2p dot big, then it is going to be after pressing 2p, I am going to be into certain state, and then after pressing big button, I will be going into TT. So then again 2p, then big, then collect TT. This will also hold over there. Okay, 1p dot little. So you look at these machines, behavior of these machines, which property will hold and which property will not hold on this machine. So if these sequences of operations are going to be performed as they are over here, then this is going to hold, otherwise it is not going to hold. So remember, this is the expression which you are going to insert into the concurrency workbench. So in the first exercise to your lab, whether you have understood it or not, I will ask it into the next class again, and we will elaborate on this further. But you have to use the tool and you have to define the vending machine in the different way I have told you today. And then you have to write these properties as a new property, and your instructors will assist you how you are going to write these properties. And then finally, with the help of concurrency workbench, you are going to find whether these are going to be satisfied or not. Okay, forget about proxy I will talk in the next lecture. Okay, so thank you all. I took little bit more time. I'm sorry for that, but that was necessary, as you can just start experimenting with these equations and these properties. So if there is any confusion, probably you can put one or two questions, and if there is no confusion, then I can end the class. Okay. Any question?